The process begins with receiving detailed measurements from an engineer. These measurements include allowances for machining, shrinkage, and material contraction during the casting process. Once the specifications are reviewed, a full-sized layout of the propeller pattern is created. High-resolution laser scanners or photogrammetry capture the exact shape and dimensions of the vessel stern. This data helps in designing and customizing the duct to optimize hydrodynamic performance, ensuring maximum energy savings and efficiency. The delivery of the Becker twisted fin involves transporting the pre-manufactured energy-saving device to the installation site. It arrives as a precisely engineered structure designed based on the vessel's scanned stern geometry. The 3D scanning of the Becker twisted fin verifies its dimensions and shape, ensuring it matches the vessel's stern geometry. This step ensures precise alignment, optimizing hydrodynamic performance and energy efficiency before installation. The preparation for fin adjustment involves modifying the Becker twisted fin based on 3D scan data to ensure a perfect fit. Precision cutting, grinding, and alignment checks are performed to optimize hydrodynamic efficiency. Tailoring the fins is a crucial step to ensure the Becker twisted fin fits the vessel's stern geometry precisely. Based on the 3D scanning data, adjustments are made to optimize hydrodynamic performance and energy efficiency. This process includes precision trimming, shaping, and surface refinement to ensure seamless integration with the hull. Engineers and technicians use computer-aided design (CAD) models to guide modifications, ensuring that the fin's curvature and angle align perfectly with the vessel's specifications. Advanced machining techniques such as milling, grinding, and welding may be used to achieve the required shape. Additionally, structural reinforcements and stress analysis are performed to ensure the fin withstands high water pressure and operational loads, contributing to enhanced fuel efficiency and vessel performance. Final positioning of the Becker twisted fin is a critical step to ensure optimal alignment and hydrodynamic efficiency. Using the 3D scan data and CAD models, engineers carefully position the fin at the stern of the vessel. Laser alignment tools and measurement systems verify its placement, ensuring it meets design specifications. Temporary supports or jigs may be used to hold the fin in place before welding. Precise positioning is essential for maximizing energy savings, reducing fuel consumption, and improving vessel performance. Welding secures the Becker twisted fin to the vessel's stern, ensuring structural integrity and durability. Highly skilled welders use specialized techniques such as metal inert gas, MIG, or submerged arc welding, SAW, to create strong, corrosion-resistant joints. Multiple weld passes and inspections ensure uniformity, minimizing stress points and ensuring the fin withstands hydrodynamic forces during operation. Magnetic particle testing, MPT, is a non-destructive testing, NDT, method used to detect surface and near-surface flaws in the welded joints of the Becker twisted fin. A magnetic field is applied and iron particles are spread over the welds. Any discontinuities create visible patterns revealing defects like cracks or porosity, ensuring the weld's integrity before final approval. The Becker Mewis duct, BMD, is a hydrodynamic energy-saving device that was developed to enhance the fuel efficiency of large, slow-moving vessels such as tankers while simultaneously reducing harmful emissions. The development of the Becker Mewis duct began in 2007 with the goal of creating a solution that would outperform existing energy-saving devices in the maritime industry. The concept was based on improving the overall hydrodynamics of a vessel's propulsion system, thereby optimizing fuel consumption and minimizing environmental impact. The development of the Becker Mewis duct was driven by the need for a more efficient energy-saving device for large vessels operating at low speeds. The traditional methods of improving propulsion systems were not sufficient to address the complex issues of energy loss caused by turbulence, vortex formation, and wake interference. Therefore, the focus was placed on creating a device that would reduce these losses without relying on rotating parts, which could be prone to maintenance issues. Reduction of hydrodynamic losses. The device needed to reduce energy losses due to wake and vortex formations, which significantly affect fuel efficiency. The approach combined two established components, a pre-swirl fin and a nozzle. The pre-swirl fin, known for its ability to reduce vortex losses, was paired with a nozzle that reduced wake field losses. Non-rotating components. To further enhance reliability and efficiency, the design eliminated any rotating parts, which are commonly found in traditional devices, to minimize mechanical wear and maintenance. By combining these two principles, the Becker-Mewis duct achieved significant fuel savings of up to 8%, which directly contributes to reducing the environmental impact of shipping operations. The successful design was validated through computational fluid dynamics, CFD, calculations and full-scale testing, proving that the combination of the pre-swirl fin and nozzle was highly effective in improving fuel efficiency. The installation of the Becker-Mewis duct is a well-coordinated process that takes place during the vessel's dry dock period, typically every 5 years for class inspections. The device is delivered in 2 parts, which are then assembled on-site in the dry dock. Since the duct is made of steel, it is adaptable to different shipyards worldwide and can be assembled and installed in a variety of locations. Once the tanker is positioned in the dry dock, the installation process begins. The ship is washed and the propeller is removed to make room for the Becker-Mewis duct. The device is then carefully positioned, with precise adjustments made to ensure the correct alignment. The installation is supervised by a VMS service engineer who oversees the process to ensure that the installation meets all class requirements and quality standards. The duct is then welded into place, with all joints undergoing damage-free testing to ensure a secure and durable fit. The Becker-Mewis duct offers several key benefits that contribute to both operational efficiency and environmental sustainability. Fuel savings and reduced emissions. The most significant benefit of the Becker-Mewis duct is the fuel savings, which can reach up to 8%. This translates into less fuel consumption, resulting in reduced CO2 emissions and a smaller carbon footprint for the vessel. Improved stability and reduced vibrations. The design of the Becker-Mewis duct helps to reduce propeller pressure impulses, leading to a noticeable reduction in vibrations throughout the ship. This contributes to greater comfort and stability both for the crew and the vessel's overall performance. Better course stability. The device also improves the vessel's ability to maintain a steady course, which reduces the need for additional power to correct the ship's trajectory. This further contributes to fuel savings and enhances the overall efficiency of the vessel's operation. The world's first class-approved 3D printed ship's propeller, the WA Impeller, represents a groundbreaking achievement in the maritime industry. Developed through a close collaboration between Ramlab, Propeller, Autodesk, Bureau Veritas, and Daman Shipyards, the WA Impeller is produced using wire arc additive manufacturing (WAAM) techniques. This advanced manufacturing process allows for the creation of complex metal parts with remarkable precision and strength. The journey began with a propeller designed by Propeller, which was then transformed into a detailed 3D printing plan using Autodesk's PowerMill software. The propeller was made from 2.6 kilometers of nickel aluminum bronze, printed in 298 layers over several days at Ramlab in Rotterdam. After printing, advanced 3D scanning methods were used to ensure the propeller met the necessary specifications. Once completed, the WA Impeller underwent a rigorous testing and trial program, including crash tests and performance trials, to ensure its reliability and durability. These tests confirmed the propeller's suitability for real-world maritime use, and it received class approval from Bureau Veritas. This certification marked it as the first-ever class-approved 3D printed ship's propeller. The WA Impeller, with a 1.35 m diameter and a weight of approximately 200 kilograms, is a significant milestone for the maritime sector. At the Ronin facility, propellers are cast on-site with attention to detail. Each propeller begins with a precision-carved mold tailored specifically for the individual design requirements. This process ensures that the propellers meet exact specifications, critical for optimal performance in seafaring vessels. After casting, the propellers undergo hand grinding, a meticulous finishing process that guarantees they achieve the precise measurements and properties needed for a long service life. Additionally, Ronin specializes in the repair and reconditioning of damaged propellers, restoring them to their original state. This expertise is part of VILJA's broader commitment to delivering high-quality propulsion solutions for ships worldwide. Testing a propeller involves several key steps, beginning with the preparation of the forming sand-clay mixture. This mixture, typically composed of sand, clay, and water, is critical in creating the mold. The sand provides the necessary structure, while the clay acts as a binder to hold the sand grains together. The water helps activate the clay, making the mixture moldable and ensuring it retains its shape during the casting process. Once the sand-clay mixture is prepared, it is used to create a one-use foundry mold. The mold is crafted by packing the sand-clay mixture around a pattern, which is a replica of the propeller to be cast. This pattern is removed after the mold is formed, leaving a cavity that precisely matches the shape of the propeller. The mold is then carefully split open to remove the pattern, and the two halves are reassembled to form a complete mold ready for casting. Next, aluminum is melted in a furnace to the appropriate temperature, typically between 660 degrees Celsius and 700 degrees Celsius, where it becomes a molten liquid. This molten aluminum is then carefully poured into the mold cavity through a funnel-like opening, filling every part of the cavity that will form the propeller. After the aluminum has cooled and solidified, the mold is broken away to reveal the cast propeller. This final product may undergo further finishing processes such as trimming, machining, and polishing to achieve the desired shape and surface finish. The MMG Propeller 1700 TEU container ship is a modern maritime vessel designed for efficient cargo transport. Built at the Wenchong shipyard in Guangzhou, China, this ship exemplifies contemporary shipbuilding practices and advanced engineering. It is equipped to carry 1,720 20-foot equivalent units, TEU, making it a mid-size container ship that serves crucial routes in global shipping networks. A key feature of this ship is its German-made MMG propeller. MMG, Mecklenburg Metallguss GmbH, is renowned for producing high-performance marine propellers, and this ship benefits from their cutting-edge design. The propeller, with a diameter of 6.5 m and a mass of 28.5 tons, plays a critical role in ensuring the vessel's propulsion efficiency. This large and heavy propeller is engineered to deliver the necessary thrust to move the ship through various sea conditions, including storms and high waves, ensuring stability and performance even in challenging environments. The ship is powered by a robust main engine, the 7S60MCC, manufactured by MAN B&W. This engine is a two-stroke diesel engine known for its durability and efficiency, with a power output of 16,000 kilowatts at 105 revolutions per minute RPM. The engine provides the necessary force to propel the ship at sea. The combination of this powerful engine and the MMG propeller allows the vessel to achieve optimal speed and fuel efficiency, which are critical factors in commercial shipping. The vessel's construction at Wenchong shipyard highlights China's growing capabilities in shipbuilding, particularly in producing large, complex vessels for international clients. Wenchong shipyard is known for its expertise in building container ships, and this 1700 TEU vessel is a testament to their ability to meet global standards. The ship underwent extensive trials before being launched into service, where it faced various real-world scenarios to test its performance, including navigating through waves and simulating emergency conditions such as engine failure or fire. These trials are crucial to ensuring that the ship can safely and effectively carry out its duties once it enters regular service. Pattern making is a crucial step in propeller manufacturing, where a precise model of the propeller blade is created, typically from wood, resin, or other durable materials. This model, known as the pattern, must account for any shrinkage that occurs as the molten metal cools and solidifies, ensuring dimensional accuracy in the final product. The pattern includes intricate details and allowances draft angles for easy removal from the sand mold, which directly influence the propeller's final shape, performance, and finish. Pumping carbon dioxide into the sand mold is a process that hardens the sand by reacting with a sodium silicate binder mixed into the sand. This reaction forms a solid, rigid mold capable of withstanding the molten metal's heat and pressure during pouring, ensuring the mold retains its precise shape and details. Completion of the bottom half sand molding. The upper half involves carefully placing sand over the pattern, matching the lower half, and compacting it. This step ensures a precise fit and completes the mold cavity for casting. Poking holes in the sand mold creates pathways for carbon dioxide to be evenly distributed, ensuring thorough hardening of the mold. Pouring molten metal involves heating it to a liquid state, then carefully ladling it into the mold. This step requires precision to avoid air bubbles and ensure the metal fills all cavities. Proper pouring ensures a uniform and defect-free propeller. As the metal cools and solidifies within the mold, leaving the cast propeller overnight allows the molten metal to cool and solidify gradually. This slow cooling process prevents internal stresses and ensures the metal achieves optimal hardness and structural integrity. In the context of maintaining the operational integrity of a 2,800 TEU container ship, the inspection of the propeller contact surface is crucial. At Guangzhou Wenchong Shipyard, a meticulous check is carried out to ensure optimal performance and safety of the vessel's propulsion system. The propeller in question is a significant component of the ship's propulsion system, featuring an impressive diameter of 7,500 mm (7.5 meters) and weighing approximately 40 tons. Given its substantial size and weight, the propeller plays a critical role in the vessel's maneuverability and overall efficiency. The propeller shaft, which connects the propeller to the main engine, is equally vital. It has a diameter of 720 mm and weighs around 30 tons. The shaft transmits the rotational force generated by the engine to the propeller, making its integrity essential for smooth propulsion. The ship's main engine is a powerful MAN BMW unit, delivering a staggering 25-40 kW of power at 95 revolutions per minute. This engine provides the necessary thrust to move the ship through the water, and its performance is closely linked to the condition of both the propeller and the shaft. The inspection at Guangzhou Wenchong Shipyard involves a detailed examination of the contact surfaces between the propeller shaft and the propeller hub. This check is crucial to identify any signs of wear, corrosion, or misalignment that could impact the efficiency of the propulsion system. Such inspections are carried out to ensure that the contact surfaces are free from damage and that the components are correctly aligned, which is vital for preventing operational issues. In pattern manufacturing, EPS, expanded polystyrene, blocks are precisely milled by advanced robotic systems. This automated process shapes the blocks into detailed propeller patterns, ensuring high accuracy and consistency. In sand molding, wooden or EPS patterns are placed within a mold frame. Sand is packed tightly around the pattern, forming a precise mold cavity that captures the propeller's detailed design. The casting process involves melting up to 18 tons of special copper-nickel aluminum alloy in a furnace. The molten metal is then carefully poured into the prepared sand mold, ensuring uniformity and strength. After casting, the mold is broken to reveal the solidified propeller. The sand used in the mold is then reclaimed and processed for reuse, minimizing waste and promoting sustainability in the manufacturing process. Machining involves precisely cutting and shaping propellers up to 3.5 m in diameter. This process refines the blade foot and other critical components, ensuring exact dimensions and optimal performance for the final product. Robotic grinding is employed to achieve a smooth and uniform surface on the propeller blades. The robots precisely remove excess material, refining the blade's contours and ensuring consistency across the entire surface. Handmade polishing involves meticulous final surface adjustments, where skilled craftsmen fine-tune the propeller's finish, ensuring a flawless and smooth appearance. Blue fit test and assembly are the final checks of the end product. Propeller repair is a complex process that requires precision and expertise, and over the past 25 to 30 years, we've developed a machine that revolutionizes this task. Designed to enhance competitiveness by reducing repair time and costs, this machine allows for precise adjustments to the propeller's angle and position, accommodating a wide range of needs. Whether tightening from bottom to top or tilting the propeller between starboard and port, our machine offers flexibility that manual repairs simply cannot match. Traditional methods, which involve clamps, welding, and other manual tools, can be time-consuming and costly. The machine addresses these issues by providing a faster, more efficient repair process. Even if a propeller arrives bent or damaged, we can often have it ready within a week, depending on the extent of the damage. For propellers with bent blades, repairs are straightforward if the damage is limited to the tips. However, more severe damage near the core presents a greater challenge, though our machine is capable of handling up to 90% of cases, even restoring blades that are missing significant portions. What sets the machine apart is its ability to handle a wide range of propeller sizes, from small to those with a diameter of up to 500 mm. This versatility, combined with our unique in-house scanner, ensures that each blade is perfectly balanced and aligned. The scanner provides detailed graphs showing the pitch and condition of each blade, allowing us to make precise adjustments for optimal performance. At YPP, the manufacturing of propellers is an intricate blend of art and crafts, transforming raw materials into high-performance components. This process, steeped in tradition, utilizes methods that date back to ancient civilizations. The investment casting technique used here mirrors the approach the Egyptians employed in crafting their jewelry, involving a meticulous sequence of steps to achieve a flawless end product. The journey begins in the wax room, where wax pellets are injected into aluminum tooling. Aluminum is chosen for its high thermal conductivity, which ensures the wax solidifies rapidly. The tooling itself features water-cooled platens to maintain a consistent temperature, crucial for producing precise wax patterns. Once the wax is injected, it takes the shape of the propeller blades. Next, these wax patterns undergo a detailed assembly process. Blades are attached using a soldering iron, and automotive-grade materials are applied to create the desired root radius. The parts are then cleaned to remove any residual lubricant before moving to the dip room. In the dip room, the wax patterns are encased in a series of ceramic shells. This is achieved through multiple dips and refractory slurries, primarily composed of colloidal silica. The slurry layers are built up to form a solid shell that will withstand the intense heat of molten metal. After drying, the shells are heated in an autoclave to melt out the wax, which is then recycled. The ceramic shells, now hollow, are subjected to bakeout at 1800 degrees Fahrenheit to ensure they can endure the pouring of molten metal. The metal of choice is 15-5 stainless steel, a high-performance alloy with 15% chromium and 5% nickel. It is heated to 3000 degrees Fahrenheit before being poured into the ceramic shells. Once cooled, the ceramic shell is removed, and any residual material is cleaned off. The resulting propellers undergo a grinding operation that is both precise and artisanal. Each propeller is carefully ground to meet Yamaha's stringent specifications. This involves a multi-step polishing process to achieve a mirror finish using a sequence of materials, including stone, ceramic, synthetic plastic, corn cob treated with porcelain, and a final porcelain pin for ultimate shine. One of the final and most crucial steps is the trail edge grind, which impacts the propeller's efficiency in water. After this, the propeller is subjected to a rigorous quality control check to ensure it meets Yamaha's exacting standards. Any necessary adjustments are made by skilled propeller builders using specialized tools to fine-tune the propeller's performance. A collaborative project between Penning Propeller and FMR Shipyard focused on the construction of 386M patrol boats for the German Federal Police. Penning Propeller has been entrusted with supplying advanced propulsion systems for these vessels, which include controllable pitch propellers, a complete control system, and transmission components. A standout feature of this project is the incorporation of a hybrid drive system, showcasing the shipyard's commitment to innovation and environmental sustainability. Penning Propeller has also provided shipbuilding components that are hydrodynamically optimized, ensuring the patrol boats operate efficiently and effectively in various conditions. The design of the system emphasizes serviceability and longevity, which is crucial for the Federal Police as they aim to use these ships for over 30 years. The propellers are particularly noteworthy, being the first of their kind with 5 blades, which enhances their performance. Moreover, the system includes components that are adaptable for future use with water hydraulics should the operator choose to transition from oil-based hydraulics. Precision installation and removal of a propeller to check the blue fit is a critical process in ensuring optimal performance and safety in marine vessels. The blue fit refers to the proper mating between the propeller hub and the shaft taper, ensuring maximum contact area and load distribution. This is vital for the efficient transfer of torque and to prevent slippage or wear. The process begins with the cleaning of both the propeller hub and the shaft taper to remove any dirt, grease, or corrosion that could interfere with the fit. Once clean, engineers apply a thin layer of engineer's blue, a pigment that highlights high spots, onto the shaft taper. The propeller is then gently installed onto the shaft, rotated slightly, and then removed. The pattern left by the blue dye on the hub indicates the quality of the fit. A uniform blue transfer across the entire surface signifies a good fit, while uneven coverage suggests the need for further adjustment. If the fit is not satisfactory, the high spots on the hub can be carefully scraped or machined until a near-perfect fit is achieved. The process of applying blue, installing, removing, and adjusting is repeated until the desired fit is obtained. This precise fitting procedure is crucial as it ensures the propeller remains securely attached during operation, reducing the risk of vibrations, shaft misalignment, or catastrophic failures. Achieving a perfect blue fit ultimately contributes to the longevity and efficiency of the propulsion system. The launch of the Hansa Australia, a 3,600 TEU container ship, marked a significant milestone in the maritime industry. Constructed at the renowned Shanghai shipyard on Chongming Island, this vessel is a testament to the shipyard's expertise and the advanced engineering capabilities of the modern shipbuilding industry. With a length of 239 m, a breadth of 32.2 m, and a mold depth of 19.20 m, the Hansa Australia is designed for efficient container transport across global trade routes. The ship's scantling draft of 12.5 m allows it to carry a substantial load while maintaining optimal stability and seaworthiness in various sea conditions. The vessel is built to accommodate 3,620 foot equivalent units, TEUs, making it a medium-sized container ship well suited for routes that demand high-frequency and flexible services. At the time of launching, the Hansa Australia had an approximate weight of 15,000 tons. This weight includes the hull structure, essential machinery, and other integral components required for the ship to float and be maneuverable. During the launching process itself is a critical phase in shipbuilding, requiring meticulous planning and precise execution to ensure the vessel enters the water safely. Given the significant mass of the ship, sophisticated launching techniques such as the use of a slipway or floating dock would have been employed to facilitate a smooth transition from the shipyard to the water. This event not only highlights the shipyard's ability to deliver large-scale, high-quality vessels but also underscores the ongoing development and innovation in ship design and construction. The Hansa Australia is now set to begin its operational life, contributing to global maritime trade and reflecting the excellence of modern shipbuilding practices.